The title of the presentation is Synthesis and Equivalence Checking. With great pleasure, I'd like to introduce Ankush. Ankush is a synthesis fellow at Cadence Design Systems, leading and managing the front-end and infrastructure teams for digital implementation. He has been with Cadence for more than 18 years and a global leader in digital synthesis and led all aspects of synthesis software development. His current research interests are high-level optimization, distributed synthesis, machine learning, and early physical and congestion-aware synthesis. Ankush is a graduate from IIT Bombay, both BTech and MTech, and he will be available to answer a few questions after this presentation. Over to you, Ankush. Thanks.
Good afternoon, everybody. Thank you for being here. My name is Ankush Sood, and I'm a synthesis fellow with Cadence Design Systems. I really appreciate this opportunity to talk to you guys, and I see that there are lots of exciting papers submitted in the VLSI Design Conference this year. Especially in the EDA track, I saw themes around equivalence checking, AI and ML, and optimization. So I decided I should share some of my experiences and learnings with you guys on the topic today. So these are exciting times for EDA and the semiconductor industry in general. So there are all these macro trends which are driving growth across the board. So you have data center, IoT, automotive, and AI and ML. So these are areas which require deep integration of software and semiconductors, and EDA tools are making that happen and really driving growth for our industry. So there are new system houses which are driving rapid innovation in this area, like Apple, Google, Facebook, Amazon, Alibaba. They weren't making chips just a while back, but they all are in the chip game today. And that's driving innovation. That's driving the rate of innovation as well. So we are producing new silicon much faster than we used to before. Even the existing players are not sitting idle. They're making big investments. They are improving their designs, and they are competing with these system houses in all aspects. So all EDA companies are growing because of that. And the exciting times are going to continue. I think there is still a lot of work to be done in this area. There's still going to be a lot of requirement from EDA to deliver on various aspects and on various technologies for lower nodes, for 3D IC, and various other things. So I work on synthesis. So synthesis is basically where it all started for digital design, right? So you have your RTL, but you need some compiler which is going to convert your RTL into gates, into synthesizable gates, and into placeable gates. So one of the trends that we see in the industry is that RTL is becoming more and more like software. So of course we have the C-level, high-level synthesis kind of paradigm, but even with system Verilog, the kind of RTL engineers are writing today is very different from the ultra-optimized RTL that we would have seen a few years back. So the size of the IP is growing. So the IP gates per developer is exponentially growing. And to do that, developers are writing better, compact code. And System Verilog really allows you to do that. So these are all these abstract coding styles with 2D structural arrays. You have deep nested loops, heavy use of for and generate statements. So all that is driving RTL to look more and more like software. So this presents a lot of challenges for synthesis. So of course you have the traditional logic level problem, and that's kind of greater than ever before. Power is becoming a big deal, right? So it's not an afterthought. You cannot optimize power right at the end of the floor or try to recover it purely at the architecture stage when you design your RTL. Synthesis tools have had to keep up with that. And of course you want to shrink your die as much as you can. So all this requires advanced compiler level optimizations. So this is something that, just like you have C, C++ code and GCC optimizes that, similarly, synthesis tools optimize your RTL and make it ready for the technology that you're targeting it for. So there are lots of these advanced compiler optimizations that, work on your RTL to give you better PPA, things like speculation, things like CSA, and even like BDD optimizations on your mux chains. So all this is done to improve power performance in EDA. So why is synthesis so important, right? Why is high-level optimization so important? So I always talk about this inverted pyramid structure. So you have your RTL at the top, and then you go through all the different steps till routing, and that's how you would implement a design. So of course, RTL is where your architecture level decisions are made, and that is the most important. But as you go down, the amount of room that you have to optimize keeps reducing. So at the one end, you have the maximum optimization scope at the top, and then you have the maximum accuracy at the bottom. So we obviously, work, in this space to kind of try to reduce the gap as much as we can. But the key thing is to remember that the decisions you have to make early on have the biggest impact on your PPA. So at the high level optimization point of view, right? So you have elaboration, you have these high level optimizations with CSA, with even transformations which are almost like algorithmic changes for your particular design. And then you go into physical aware technology mapping, incremental optimization. So these architectural transforms that are made during HLO have the biggest impact on PPA. Once you have made some of these decisions, you cannot revert them back. So that's why it's very important for the synthesis tools to understand that and make the right decisions upfront. So here is an example of what I call an algorithmic transformation in high-level optimization. So this is a very standard RTL, right, coding style, and you would see that in all sorts of designs from networking designs to GPUs to CPUs. You'll see this kind of design all over the place. So these are what I call typical for loop unrolling for conditional computation for n iterations, right? So it's conditional. So you have this mux set after every stage, which is basically deciding whether you take a function of the previous value or the previous value. And it's a very simple coding style, so you wouldn't think twice when you do this. But once you convert that into hardware, it becomes a long chain of these operators, which is very hard to optimize and which will be limiting your frequency and power. So there are really two ways that we can transform this algorithmically. On the left-hand side, you have an option where you can actually select the needed data upfront and then just compute once. So this is very good for area because the computation is done once. And on the right-hand side, you have another option where you can compute all your choices upfront and then select one, which is typically best for timing, especially if your paths are critical to the select of these big muxes. So how do you decide which one to pick? Of course, you cannot make that decision in the RTL unless you're iterating. Maybe you can iterate n number of times and then figure out that, okay, this kind of a coding style will work best for me. But these are decisions which are best made in the context and also which should be PPA aware, right? So you want to do these decisions based on the best PPA possible. So at Cadence, we've been working on developing this ROI-driven architectural exploration, and the idea is very basic and very simple. So what we want to do is that we want to align whatever optimizations we make at the HLO level with the next big step in the digital implementation flow, which is placement. So we know that placement really cares about TNS. So a lot of what we do is aware of TNS, but it's also aware of what we call TNS sensitivity, which basically kind of is a measure of how much improvement in TNS can you make by getting a small improvement at a particular node in your graph, right? So if I make a 1 picosecond improvement here, will I get a 1 picosecond improvement there, etc. Right? So that is basically the simple metric that we use to drive architecture exploration. And the way I always explain it, you have, this kind of zone where if the slack is very negative or the slack is very positive, you will make certain decisions, right? So if the slack is very positive, you'll go after area and power. If the slack is very negative, you still have to go after power, but you'll be kind of limited by the timing. And in between, you have this big trade-off zone, and that is where the analytical engine and the costing framework really plays a role. So you have all these different cost vectors now with normalized slack, with TNS sensitivity, congestion, this is something that we really have to care about, and power. So it's amazing, we have to look at all these different things so early on in the flow. And this is again, as you can imagine, that since there are so many of these trade-offs and you need so many of these models, of course, machine learning can have a nice role to play there as well. So next thing is data path optimization. So this is where, the equivalence checking becomes the most complex. So you have a big RTL module, and within that RTL module, you have a computational part of it. So you're basically doing some multiplications, additions, divisions, and subtractions, right? So this computational part, this arithmetic part, is what we call the data path cluster. And once you take this data path cluster and some of its surrounding logic, it becomes a data path region. Now, for every data path region, we have multiple different configurations that are possible to optimize the design. So these are essentially various points on that area, delay, power trade-off curve. So all these optimizations can produce various different levels of improvement in your design, right? And they also create kind of different levels of complexity for your logical equivalence. You could be doing something where you are improving your timing, or you could be doing something where you are sharing as much of the logic to improve your area. And this you can do in context. So there's no single way of doing that. In any given design, we might be doing this in various different ways in various different parts of your design. So this is a very, very, very large solution space. And we're talking about, high level constructs like adders and multiplier. A single multiplier can be like 50, 60,000 gates in your design. So these are very complex structures. And each individual optimization, like resource sharing, is very, very hard to verify for logical equivalence checking. But once you do a chain of these optimization, right, you kind of do them one after the other, it becomes really, really hard because your final circuit hardly looks anything like what you started with. So it's kind of a complete algorithmic transformation in some cases. So what's the challenge for the EDA developer, right? So logical equivalence challenge is there, of course, when you are trying to verify the circuit, but what's the challenge for the synthesis guy? So his job is to do all these transforms and ensure that they will be verified. But his job is also to ensure that you cannot create a non-equivalency in your design. Of course, you want to be right by construct, but you make mistakes. So you want to figure out upfront that I have not made a mistake across any sort of variable input that I might get. See, these non-equivalents really hurt a lot. So at the one end, it's a big, big challenge to debug them, but also it can impact schedule and it can impact tape outs. So what we really want to do is that we want to ensure that we are correct by construction. So when we ship our software, our customers don't see any non-equivalences. But at the same time, we are pushing the envelope on PPA, right? So the more we push the envelope, the harder it is going to get to verify these transforms. As I already mentioned, this is a very large solution space, and we want to ensure that every possibility is taken care of, and we test every possibility before we ship, which is basically kind of impossible, right? So here's an example, right? We have this transform which takes an adder, which is padded, and feeds into a CSA, and we convert it into a padded adder, which feeds into a CSA. It's a very simple optimization. So the whole idea is that we're trying to improve timing using this. But there are these 5 independent parameters in this one single optimization. And, once you look at all the parameters and all the inputs, the solution space explodes, right? So there can be 331,000 different test cases to run if you want to be sure that you are clean across the board. And that's very hard. No human can generate all these test cases. So what we think is the right way to do is to kind of build more of this testing into the software itself. So we call this an automated testing framework. So the whole idea is that your software really knows what are the patterns it's working on. Since it knows what patterns it's working on, it can actually spit out all the patterns that it will ever encounter. And we can actually iterate over the space and figure out all the patterns up front. So the idea here is that, we leverage our C++ macro templates that are built into the tool. And from that, we figure out what are the patterns that we would have to test on. And then, of course, we use a Python kind of a framework so that, for all these patterns, when we create a Verilog and a LEC do file, we can actually run it and verify that, the output is equivalent or not. Of course, it's still 331,000. So even doing this automatically over the farm, distributed, all that stuff we do, it still can be very slow. What you do get out of that is that you get a strong confidence that in what you have written is actually going to work, right? So since it's 331,000, we have to be smarter about the whole thing, right? So one of the areas that we have been working on is pruning the operator symmetry. So for example, if you have A plus B, you don't need to verify a 2-bit value with a 4-bit addition versus a 4-bit value with a 2-bit addition, right? You don't have to verify all these separately. So that can really help you reduce the space because, it cuts it by almost 3x. But then, we have been actually working on this for a while. So one thing we realize is based on experience, you can say, or based on some, testing that we have done internally, that a lot of these non-equivalencies happen at the corner conditions. So this is actually very interesting because the corner conditions are much lower in number. So what we have done is that we have biased our test case selection. We do some random test case selection to be more biased towards the corner conditions. So we cover more or almost all of the corner conditions, and we cover less of the conditions in the middle. And that helps us to reduce the 100,000 to 40,000. So this is now a bit more manageable, and we have to do this over 3,000 or 4,000 of these optimizations that we have. So we can run it like over a week or 2 weeks over the farm, over the cloud, whatever way we want to reduce and actually get that confidence that our solution works. So, I just wanted to give a very quick idea about synthesis, what we have been doing for optimization, but also what's the challenge for Abbasi. So we can talk about this for hours, but this was a quick introduction because we always think of equivalence checking as a problem for the EDA developer who is doing the equivalence checking, but it's actually equally big a problem for the synthesis developer as well. So hope, you guys found some of this information useful. So one thing I'd like to say to conclude, right? So synthesis is even more relevant now than it was ever before. It's simple, right? So you're doing all these, AI, ML chips, which have a lot of mathematical transforms and which are doing a lot of computation, and you want to do that at the least amount of power and area. So synthesis really plays a big role there. And as I said, right, the choices that you make early on, you have to stick with them, and then they really have a huge impact. The LEC challenge is there, but it's not unsurmountable. I think if you are smart and if you are building software which has better test pattern generation built into the software, you can do a much better job. So ultimately, it's about automation and it's about parallel distribution. So you have to do that. That's it for me. Thank you very much. Thank you for giving me this opportunity. I hope you enjoyed the talk and best of luck for the rest of the conference. Thank you. Bye-bye.
Thanks, Ankush. That was excellent. There are a couple of questions, Ankush, if we can take a few minutes of your time. One is a question to get your thoughts on the use of machine learning in EDA tools for coming up with recipes for synthesis and equivalence checking, so as to essentially get the most optimized recipe for a design.
Sure, Adil. Yeah, sorry, Taher. Thank you. So actually, that's a very interesting question, and this is something of kind of a lot of interest to us at Cadence as well, and I think other industry players are also looking at that. So since EDA software is not quite like your standard consumer software, so this is built with a lot of bells and whistles, and a lot of customization. So usually when we ship software, we might have, let's say, 100 user settings that we expose to our users to play around with PPA, but we might have 1,000 in the factory, which we haven't exposed. And all of them, they become like test case specific. They give you the best PPA for a certain class of test case, depending on the timing constraint or the power constraint or the power domain, the 1801, etc., whatever, right? So they might give you different PPA profiles, and we cannot expose everything to the user because the solution space is just exponential, right? It's very, very hard to figure that out. So this is where machine learning is really playing an amazing role, right? So we have what we call Cerebrus, right? So this is built around the Cadence tools. So this is what we call machine learning outside, right? So it's built around the tools which can play around with these options. And we have seen like 10, 20% PPA improvements, right? In some cases. So that's kind of, with the compute becoming cheaper and the designer time becoming more and more expensive as well as harder to get, I think this is the way to go. And we have started actually building a software, keeping the machine learning piece in mind, so that we put in the tuning variables and the tuning options right into the software when we know that there is no way to make a best decision based on the test suite that we have. So it will be dependent on the designs that we're going to get from the customer. So that's actually something that we are really investing in, and it's looking really good.
Excellent. Thanks. We have time for one more question, Ankush. The question is that as we move to smaller geometries like 4 nanometer, are there any new challenges in synthesis which are not there, say, at 8 nanometer?
Actually, synthesis is to somewhat, some extent, kind of reasonably independent of the technology node, at least, from purely from the physical aspects of it. But then the other aspects, right? So depending on the technology you node, your library might behave very differently, right? So at like a higher node, the 28 nanometer, etc. Leakage used to be very important, and people would really care about that. But with FinFET, leakage has become less important, and it's all about dynamic power optimization. So that's one part of it. Then also with lower nodes, the technology is becoming more and more interesting. We don't have this kind of unified view of the synthesizable cells anymore. You have these hybrid cells which have double the height, and they have different sorts of requirements for the physical part of the flow. And we have to actually balance all of that in synthesis upfront so that we can kind of make the netlist that we produce much better for placement, much better for dynamic power optimization, much better for all these. So it might not be quite obvious, like that link might not be obvious at the first level, but at the second level, yes, of course, every time a new node comes, we have to do something in synthesis to account for that in various different ways.
Got you. Thanks so much, Ankush, for your time. And that was fantastic. I'd like to sort of introduce the next presentation right now. It is Equivalence Checking of Non-Binary Combinational Netlist by Aditi Singh from IIT Kharagpur.
Hello everyone, I am Aditi Singh and I will present my paper titled Equivalence Checking of Non-Binary Combinational Netlists. The presentation is organized as follows, starting from a brief introduction and motivation, followed by the problem description. Next, the proposed algorithm is explained in detail. Finally, we will look at the experimental results and conclusion. Let us begin. Equivalence checking for combinational circuit has been an active research topic in the formal verification of digital circuits for several years now. Many state-of-the-art industry-level techniques for combinational equivalence checking have been proposed and implemented, including a pure binary decision diagram approach, simulations, and Boolean satisfiability solver, that is a SAT solver. The only constraint is that all these tools work on binary logic. The optimization techniques used in these solutions also exploit the Boolean nature of the logic netlist. In real-world applications, though, X value is propagated in the circuit, checked for equivalence. X value is an unknown or potentially non-deterministic voltage level. One such application is RTL synthesis. In RTL synthesis, X value arises mainly because of two situations. First, the X value is specified in the RTL code by the designer, for example, the default condition in a case statement or don't care conditions, or if the X value is due to an undriven signal. In these situations, the X value will propagate through the circuit and may result in an X valued output. The RTL synthesis tools, though, exploit the X value terms in the hardware description language to reduce the size of the synthesized circuit, such that the synthesized circuit will never have an X valued output. Thus, the existing CAC tools will result in a false negative on equivalence checking of the specified RTL and synthesized circuit. The motivation of this paper is to solve such problems using the existing state-of-the-art CAC tools efficiently. Equivalence checking for binary logic netlist is simplistically defined. For the equivalence of two circuits, the corresponding output should have the same Boolean value for all possible input combinations. Binary decision diagram based combinational equivalence checking involves the construction and comparison of canonical, which is unique BDDs. Ordered binary decision diagrams provides one such canonical representation, and reduced order binary decision diagrams is a result of the optimizations of the OBDDs. CODD uses pointer-based ROBDD manipulation, and in case of equivalent circuits, both the constructed ROBDDs have the same head pointer. This makes equivalence checking a fairly simple process. In the presence of X value, though, the definition of equivalence is more exhaustive. For developing the equivalence model for X-valued netlists, it is considered that the inputs have Boolean values 0 and 1, and the netlists have no floating signals. For two combinational circuits having the same inputs and outputs, we define compatible equivalence for comparing the output values. For netlist A to be compatibly equivalent of netlist B, all the outputs corresponding to netlist B of netlist A should satisfy these conditions. First, if the output of netlist A has a fixed Boolean value of 0 and 1, then the corresponding output of netlist B should also have the identical Boolean value. For example, 0, 0, 1, 1. But if the output of netlist A has an X value, then the corresponding output of netlist B can have any value, 0, 1 or X. If these conditions are satisfied, then netlist A is said to be compatibly equivalent to netlist B. On the contrary, if netlist A has a fixed boolean value for its output, that is either 0 or 1, and the netlist B has a non-identical value of that particular output, then the two netlists are non-compatibly equivalent, or in other words, are not equivalent. Moreover, if the output of netlist A has a fixed boolean value, that is 0 or 1, whereas that particular output of netlist B has an X value, then too both the netlists A and B because of that particular output are non-equivalent. As said in the previous slides, the input values are always considered to be boolean, that is 0 or 1. Then how is X value injected and propagated in the circuit? The algorithm considers that X value is injected in the circuit through DC gates. DC gates has two inputs, that is an input and an enable, and an output. A circuit can have multiple DC gates. Although inputs are strictly boolean, X values are introduced in the circuit because of this particular DC gates, which may get propagated to X valued outputs for some cases. DC gate is the only source of X value injection in the circuit. Looking at the HDL and the truth table, we can see that the output is equal to the input if the enable is 0. But if the enable is 1, then the DC gate is said to be in the undriven state and the output is X for all values of input, that is 0, 1 and X. We now move on to the X value CEC algorithm. This paper proposes an approach which aims at solving the X value equivalence checking problem by modifying the pre-existing Colorado University decision diagram package for binary decision diagram manipulations. CODD is capable of constructing BDDs for variables count as high as 300 in milliseconds. The proposed solution takes two combinational netlists in the form of Verilog files as input. The netlists are composed of AND, NAND, OR, NOR, XOR, XNOR, NOT, BUF, MUX and DC gates. In the proposed solution, new variables are introduced in the BDD for every X value injecting DC gate. The algorithm has three steps, which are pre-processing step, the BDD formation step and the equivalence checking step. Let's look at all these steps one by one. The pre-processing steps involves the taking of Verilog files and using the Verilog parser to assign a unique ID to the input ports, output ports and temporary wires of the module. It also shows the input count and the output count. The output of the preprocessor is the circuit corresponding to the Verilog files. These circuits contain details about the gates of the netlist and also another important quantity, which is the DC count. The first DC gate encountered in the module has a DC count set to 1 and so on till the nth DC gate, which has a DC count of n. The number of additional variables is equal to the total number of DC gates and in this case it is thus n. The circuits created in the pre-processing step are fed to the BDD formation function one by one to form two BDDs per output corresponding to netlist A and netlist B. These BDDs are compared in the next step of the algorithm, which is the equivalence checking step. The BDD is formed recursively using the Colorado University decision diagram package, which allows for direct formation of a BDD given the type of the gate and the input and output BDDs or variables of that gate. The inputs of the module are the variables for the BDD construction. Also, there are additional variables. Thus, the total number of input variable count is the sum of the primary inputs plus the additional variables. The recursive algorithm uses the intermediate BDDs of the temporary wires to construct the final BDD of the output of the circuit. While Colorado University decision diagram provides direct support for all other gates, the MUX and the DC gate are implemented using the ITE, which is the if-then-else construct. For DC gates, the BDDs should insert an additional variable when the gate is in the undriven state, that is, when the enable is 1. This can be seen in the form BDD function, in which if the type of the gate is DC, then we use the ITE construct in which the enable, which is the input 1, if it is 1, then the output is an additional variable and the particular additional variable which is used depends on the DC and count. The recursive BDD function is used to construct the BDDs recursively, starting from the primary output and going towards the primary input. Now we move on to the final step, which is the equivalence checking step. The output BDDs obtained in the previous step are compared for equivalence. Similar to traditional approaches, a mitre is constructed for each of the output. A mitre is nothing but an XOR of the corresponding outputs of the two netlists. The two given netlists are non-equivalent if there exists at least one true evaluation of the mitre wherein all the additional variables have an X value. This is because if there is a true evaluation of the mitre in which the additional variable does not have an X value but instead has a fixed Boolean value of 0 and 1, it means that the mitre evaluates to false when we complement the value of this additional variable. Thus, the output in the original circuitry for that particular combination of input variables is not a Boolean value but an X value. According to the rules of compatible equivalence, this set of input values cannot declare that the two netlists are not equivalent, as an x-valued output is equivalent to any value of output for corresponding netlist B, which is 0, 1 or x. On the other hand, if there exists at least one true evaluation of the mitre for which all the additional variables have an x value, it proves that the x value has not propagated to the output, and still the outputs of netlist A and netlist B are different for that particular input combination. Thus, the two netlists are proven to be not equivalent based on this input set. Now, to identify whether the additional variables are all x valued for at least one of the true evaluations of the mitre, we use the concept of Shannon cofactoring. The mitre is cofactored with respect to the additional variables to obtain the positive and the negative cofactors by setting the additional variable to 1 and 0 respectively. A true evaluation of the BDD formed by the intersection, which is an AND of the positive and negative cofactor, proves that the additional variable is x valued for the true evaluation of the original mitre. This process is repeated iteratively for all the additional variables. If the final BDD thus obtained is not 0, or in other words, it evaluates to true for at least one input combination, then the two netlists are not equivalent on the basis of this particular input combination. For all the other cases, the two netlists are equivalent. In order to understand further, let us look at an example. Circuit 1 and Circuit 2 are checked for equivalence. Looking at Table 1, we can see that both these circuits are compatibly equivalent, because when the Circuit 1 output has a fixed Boolean value, then output 2 also has an identical Boolean value, whereas when the output 1 has an x value, then the output 2 can have any value 0, 1 or x. Now we need to check whether we are arriving at the same conclusion on the basis of our algorithm. We calculate the outputs of the circuit considering the new additional variable, which is depicted in the circuit. This is the modified circuit whenever the enable of the DC gate is set to 1 and we are adding an additional variable. Now we construct the truth table by using this additional variable, which eliminates any x value in the output. This is shown in Table 2. We observe that for input 001 and 100, the mitre, which is the XOR, evaluates to true. But when we complement the additional variable for this particular cases, that is 000 and 101, the mitre evaluates to false. So, this indicates that the value of the additional variable is not x for the true evaluation of the mitre. Thus, according to our algorithm, the circuits are equivalent, as seen in Table 1 as well. Moreover, if we consider our Shannon cofactoring approach as well, we arrive at the same conclusion. We calculate the positive and negative cofactor of the mitre with respect to the additional variable and perform an intersection of these two quantities using AND, and we obtain that the intersection cofactor is equal to 0. Thus, according to our algorithm, again we arrive at the same conclusion that these two circuits are equivalent. We now move on to the experimental results. The system used is an Intel Core TM i5 7200 CPU at 2.5 GHz into 4 clock with 64-bit processor. The Verilog parser written in C is compiled using GCC on Linux operating system. BDD construction and equivalence checking was implemented using the Colorado University Decision Diagram package. For verifying the proposed algorithm, we used 12 combinational circuits from the Logic Synthesis and Optimization Benchmark Suite. The Logic Synthesis and Optimization Benchmark Suite has three versions: original, optimized and swept HDL. We consider the original and optimized HDL files for equivalence checking, in which DC gates are injected into the original HDL to form the modified HDL. Table 3 shows the simulation results for equivalence checking of the modified HDL and the optimized circuit. The CPU time for the proposed solution remains in the same order even for high number of DC insertions given by the hashtag DC, which is the number of DC gates inserted. The tabulated CPU time for each case is the average of 5 different DC gate insertion combinations. We have done this to account for the dependence of the CPU time on the insertion location of the DC gate. The computation time is still much less than 5 seconds for all the circuits. In conclusion, we propose an X-value equivalence checking algorithm in this paper. The solution prevents the propagation of X value to the output by replacing the DC gate with suitable Boolean expressions limited to 0 and 1 as the input as well as the output. It allows for construction of traditional BDDs that can be manipulated using the Colorado University Decision Diagram package, which is a state-of-the-art industry-level tool with all possible optimizations. There is no need to develop a new tool that deals with the X value and can perform the memory-intensive 3-valued formal analysis. The cofactoring approach reduces the size of the BDD. It compensates for the increase in size due to the additional variables. A crucial advantage of the proposed algorithm is that the final size of the BDD, considering the X values, is same as the Boolean value BDD. It enables dealing with the X-value injection efficiently concerning CPU time and checking for equivalence using state-of-the-art Boolean equivalence checking tools. Here are the references, and that's it from my side. Thank you.
Thanks, Aditi, for the presentation. There's one question which has two subparts. Aditi, if you could elaborate on those. The first one is essentially the part one is on which platform we can perform the equivalence check which you have proposed in terms of the algorithm. And the part B is that don't care optimizations and boundary optimizations happens under the hood by logic synthesis. Do you see any challenges and solutions offered by the algorithm which you have presented?
Hello, Taher. I'll try to answer these questions one by one. So the first one regarding the platform. So as I have explained, my solution is an extension of the Colorado University decision diagram package. And this is a state-of-the-art package which deals with equivalence checking. But the X-value equivalence checking is not yet integrated into it. And that is where my paper or my algorithm comes in. As for the platform where you can access the X-value equivalence checking, as for the Colorado University decision diagram package, it is an open source platform or a tool which is available freely. But as for the extension which I have proposed, there is not yet an open source availability as of now. But maybe I would consider putting up the code, which is the Verilog parser, as well as the equivalence checker once it is, once this paper is published. Maybe I'll open source it because, yeah, that is a thing which can be considered as a future work. Regarding the next question, that is the don't care optimization in the RTL synthesis. This is exactly the problem which we're trying to solve. So in the RTL synthesis, even though the designer has specified a don't care condition, the RTL synthesis tool will optimize the construction of the circuit by exploiting this don't care condition. And thus in the final circuit, we won't have a don't care output. So when we compare these two circuits, that is the circuit which has been proposed by the designer and the final synthesized circuit by the normal equivalence checking tools, then they would be non-equivalent because of this injection of this X value. So the challenge for us is to make sure that even though there is an X valued output, we are still getting the correct equivalence result when we use the tools, when we use the equivalence checking tools. So the challenge is this, that the RTL synthesis tool will exploit this X value, and the solution is the algorithm which I proposed in this paper, which ensures that the equivalence checking gives the correct result even in the presence of these don't care or X value conditions. I hope I have understood the question correctly and answered satisfactorily.
Yes, Aditi, thank you so much. It was very good. Thank you so much. The next paper is titled "The Dynamic Variable Ordering During Algebraic Backward Rewriting for Formal Verification of Multipliers." Jitendra, Kumar, and Asutosh Srivastava are the presenters and the authors from Jawaharlal Nehru University. Over to you. Thanks.
Hello everyone, my name is Jitendra Kumar. I am here to discuss my work on formal verification of integer multiplier circuits. The project was supervised by Dr. Asutosh Srivastava. First of all, I would like to thank the conference team for allowing me to present my work at this streamed conference. I will start my presentation with the following lines. When verifying multiplier circuits, one question comes into my mind. What will you do if your multiplier has bug which has only a few counterexamples? Would you apply SAT or VDD? If you have only one counterexamples, then for SAT it will be like searching a needle into a pile of sand, and SAT will turn into an exhaustive simulation. As we know, BDD has exponential complexity with the input size, and hence it may not be a feasible solution to apply BDD. Can algebraic backward rewriting be a solution? We will get the answer by the end of this presentation. In this presentation, we will discuss how algebraic backward rewriting can be a foolproof solution to verify multiplier circuits, how it works, and what are the problems that may occur during rewriting. Also, we will see how we can overcome them. Here are the major points to be discussed in the entire presentation. A little introduction about multiplier verification, what are the algebraic expressions of circuits, how backward rewriting works, what problems may arise during rewriting, our proposed method to overcome them, the flow and the verification results. Finally, I will summarize my presentation. Now let us proceed to the next slide. If you look into data path design verification, you will see the multipliers are the complex part to verify, especially when there are only a few counterexamples to detect the bug. Foolproof verification become a challenge. Recently, algebraic backward rewriting-based verification was proposed to give foolproof verification. One major problem with algebraic backward rewriting is monomial explosion. In this work, we have tried to overcome this problem with our proposed dynamic variable ordering. Now let us move to the next slide. In this slide, I would like to brief about algebraic expressions. Equation 1 shows the general algebraic expression of the specification of an integer multiplier circuit. We can represent each gate in terms of algebraic expression as shown by the equation 2, 3, 4 and 5, where z, a and b are the Boolean variables and can have only binary values. Since the expressions are in algebraic form, the addition and subtraction are performed according to simple algebraic calculation, not according to the Boolean algebra. Now I would like to discuss how can we use these algebraic equations to identify the correctness of a circuit. Moving to the next slide. Backward rewriting. If we expand the general integer multiplier equation for 2x2 bit multiplier circuits, then the equation can be represented as integer representation of outputs minus summation of all partial products as shown in equation 5. If we perform rewriting in reverse topological order, that is replacing output specifications of a gate with its corresponding input specification, then we can reduce the specification into a zero polynomial for a correct representation, and we can conclude that circuit is bug free. Now a question arises, what happens when there are single bug or multiple bugs presented in the circuit? Let us assume that by mistake gate 4, which is a AND gate, is replaced with an OR gate. In this, the reduced polynomial will not be a non-zero polynomial and a remainder will be generated, and we can conclude that the circuit is not bug-free. Using the generated remainder, we can generate the counter examples to localize the bug. In our study, we are focusing only to detect a bug, not to localize the bug. In this way, we can conclude that unlike in SAT, without any assignment of values to the variables, we can detect the bug. As I said in the beginning, that backward writing can give foolproof verification. Here you can see even if a single bug presented in the circuit, it will turn the final specification into a non-zero polynomial. In the next slide, we will see the problem with the algebraic backward rewriting and a probable solution. Problem in rewriting. Although the final polynomial has very less monomials or zero monomial, but the intermediate monomial may explode. The rerouting is also very sensitive to the order. In our proposed method, we first tried to detect the gate pairs and adder trees by performing reverse engineering. Then we allowed local rewriting to eliminate the vanishing monomials before global rewriting. For further accumulation, we tried to change the order of rewriting at dynamic time. I will explain these points in the next slide. Moving to the next slide. reverse engineering for gate pair detection and early removal of vanishing monomials. If we look inside the circle, the gate number N45 has two input gates, N44 and N43, which are sharing the common inputs N42 and N33. If we generate the algebraic expression of N45, it has monomial, which is multiplication of N44 and N43. Since both N44 and N43 are sharing complement common input, if we multiply their algebraic expressions, then the multiplication will reduce to the 0. Hence, we can eliminate the multiplication without performing the backward rewriting. Hence, we can reduce the intermediate monomial before going for global rewriting. Moving to the next slide. In this slide, I would like to explain how we are deciding the order of rewriting at dynamic time. If you see the reverse topological order, there may be several gates at the same level. How will you decide the order of these gates? In our proposed method, we first give the preference to the gate which input has the highest preference. For example, in the figure, if we see gate N27 and N46 are at same level from output. If you look their input, the inputs of N46 have highest preference in the order of rewriting because they are closer to the primary outputs. So we give the preference to N46 over N27. Further, we put a threshold of monomials, that is, after writing a variable into the global equation, if the monomials are increased to double in size, then we will backtrack and update the order of rewriting. Here we will demote the order of the variable and we'll go for another variable that is in the key. So this was all about our proposed method, and now we will see how our simulation flow works and how we have designed the tool in the next slide. Tool flow. We have designed a standalone tool by using C++ programming language. Our tool is taking the gate level netlist in belief format and then transform it into corresponding algebraic equations of each gates. In the very next step, we perform reverse engineering to identify gate pairs to eliminate the vanishing monomials. The same step involves local rewriting and order generation. In the last step, we perform global rewriting using dynamic variable ordering. The output of the simulation is either the circuit is correct or a remainder indicating circuit is buggy. Moving to the next slide. Verification results. We have tested our design tool on integer multiplier circuits generated by Abbasi, which is an academic tool used for synthesis and verification. The table shows the percentage reduction in the polynomials. We have performed the simulation on array multiplier circuits up to 512 bits. The average reduction is approximately 24.86%. Moving to the next slide. Here are the results for simulation time. The table shows the simulation time to verify integer array multiplier circuits. We were able to verify up to 512 bits multiplier circuits generated by Abbasi. We compared our result with emulate. Although simulation time is higher than the emulate, but suddenly the simulation time for emulate for 256 and 512 bit multiplier circuits is increased and was not able to complete in the given time limit. So that brings to the end of my presentation. Now I would like to summarize my presentation. We discussed three major points. First, I discussed about algebraic backward rewriting, followed by problems in rewriting. Then we looked into the problem's solution. Finally, I presented the results We can conclude that the algebraic backward rewriting can be a way to verify multiplier circuits. Thank you very much for paying attention. If you have any question, I would like to take an opportunity to answer them.
Thanks, Jitendra, for your presentation talk. There's one question, and essentially the question is that quite often in formal verification of netlist, there is a situation where there is the formal tool, equivalence tool is not able to come to a conclusion. It essentially is neither able to identify a mismatch or equivalence or a non-equivalence and a kind of an abort situation. This approach of yours for multipliers, would that also, besides improving the runtime and turnaround time, would it also have an impact on these kind of situations where the conclusion is not clear?
Yeah, yes, sir. We have actually a few circuits that, although we are working on that also, and let's say that is like direct generation from truth table. We have very complex circuit and SAT, and of course BDD is not able to generate, because if you see more than 16-bit multiplier circuits, so the complexity of BDD exponential, so it is not able to complete the BDD generation. Other than that, we have SAT based technique, but a SAT requires actually the reference circuit somehow is structurally similar to the circuit that we are going to verify. So that would not be that is the case when we are looking if we have completely different architecture. Can this algebraic backward writing be a full solution? That is why we are working on that. Actually, we have few sets and we are working on this also.
Excellent. Thanks, Jitendra, for your response and for your time.
Taher, can I ask a question?
Yes, please, Ankush, please.
Yeah, hi, Jitendra. Yeah, very nice talk. Thank you. So I just had a question. So I saw that your reduction was approximately 25%, right, for pretty much all the different multiplier sizes.
Yes.
So when you say 512 bits or 128 bits, are you always doing a balanced multiplication, like both the multiplicands are 128 bit, or have you seen similar reductions for unbalanced as well?
No, I have actually used it, like if it is 512 bits means 512 into 512.
Okay.
Yeah.
So did you see any problems with unbalanced things? Like let's say I multiply a 32-bit number with a 64-bit number.
Yeah, we have actually not tried that also. That maybe we can try in future.
Okay. Yeah, that'll be interesting to see what your algorithm, how it works on that.
Yeah, sure.
Thank you. Thanks.
Okay. And thank you for your suggestion actually.